Our next presenter is Scott Krig. We spoke about Scott's book, Computer Vision Metrics, this morning. Scott, you should have seen the stampede when we announced we had 5 copies here for, I mean, poor Brian was practically trampled. Those of you who were lucky enough to get a copy of Scott's book this morning perhaps could get it autographed by him after his presentation this afternoon. But we've had a really great collaboration with Scott around this book. I think it's been a win for him in getting some boosted visibility for the book. It's been a win for us, bringing some interesting content and attention to the Embedded Vision Alliance website. And I think a win for our community of product creators who've learned about this book, and many of them have accessed it. I asked Scott to come and share. When you read the book, you will see an enormous amount of research and thought and experience went into it. And I asked Scott to come and share some of his accumulated wisdom, particularly on this topic of feature detectors and feature descriptors. So I realize it's a little bit late in the day to now be getting technical, but I've spoken enough with Scott and read enough of his book to know that he has an extremely crisp and cogent way of presenting this content. I think you're going to find it very accessible and very enlightening. Scott.
Thanks for the kind words, Jeff. And I really appreciate the opportunity to be here and talk about feature description. So Jeff, you asked me to kind of wake people up, and I didn't see the dark chocolate Lindor balls that I wanted to pass around. So I'll tell a really quick joke. This is going to be like a 20-second joke. And it's a technology-related joke. Does anyone remember the PDP 1170, 1134 way back? Okay. So a friend of mine told me this joke. He actually had one, and they had a core memory. Does anyone know what a core memory is? It's a round magnet, and there's a whole bunch of these with wires going through, and this is effectively memory. And he said, over time, they were noticing data degradation with their PDP system. And they weren't sure what was going on. And the memory was just gradually getting parity errors and getting worse. And finally, one bright guy took it apart, and he found a rat's nest in the core memory. A rat had burrowed in there because it was warm and built a nest. And I actually told this story to Bjarne Stroustrup one time, and he was listening to it, and he just emphatically said, rats. So we've got bugs and we've got rats. So I hope that wakes you up and gives you a little history. Yes, I actually worked on a PDP system myself. So what I'm going to be talking about is feature description. And we're all familiar with images and pixels. And the title of this presentation was picked by Jeff. And he wanted me to discuss at a reasonable level. Could I see a show of hands who is at an executive level, getting things executing? Good. Who is at a marketing level, trying to make sure we understand the feature selling thing? Who is at the design or the research level? Okay, we've got a mix. What I'll try to do is go along at a level people can understand, and every once in a while I may poke really deep, but anything I poke at that's really deep, you'll be able to get the book. There's free online copies, and you can probably go as deep as you want through the references. So we'll be talking about what is a feature. When we look at images, we're looking for things. We're looking for features. And we'll talk about invariance and robustness attributes. So keep these things in mind as we go through. And what is a vision pipeline? And we're going to take a high-speed tour here. And there are many kinds of features, many kinds of robustness and invariance attributes such as scale, perspective, distance, contrast, illumination. And there are many kinds of pipelines. We heard from Ren about the convolutional networks, the deep learning networks. There's so many different things that people are doing. The focus of this talk is more to survey in a museum. Here's the Van Gogh, here's the Michelangelo, here's the convolutional network. And maybe I'll mention the names of some of these people who are doing this state-of-the-art work as well. So the first thing that I would like to suggest is it's useful to break down feature description into a taxonomy. And there's a couple simple ways to do it. We all know what pixels are. I assume we all know what pixels are. They have color, they have intensity, and there are many kinds of feature descriptors that people build based on just the pixels. That could be a relationship between the neighboring pixels, such as a gradient. The grade on a freeway for somebody who's not mathematically oriented, how steep is it, what are the gradients in the image, what are these points of interest, what are the points that we can differentiate from a smooth background. And many of the descriptors are formed into vectors that are binary. Comparison, is this pixel greater or less than this pixel? So that's one family. The local features, they can be binary, they could be other spectra. By spectra, I just mean some numerical value, a gradient I mentioned, an intensity, there's too many. And then there's global features. These are features that you can see across a region. They're not necessarily based on one point or a gradient in an image or a spot. They are describing larger regions or features in the image. And things like histograms, you know what a histogram is. What's the histogram distribution of this image? That's a simple global method. Then there's texture and color. There are many descriptors that use these types of attributes. Then there's the shape of pixel regions, blob analysis, particle analysis, and we can get all kinds of measurements out of shape. Shape can be a very useful feature. Then there's basis sets. So what do I mean by basis? Well, we have a base 10 numeral system. We have a base 2 binary. We have pixels as a basis. We can transform pixels into the Fourier domain. So there's many different bases that can be used. It's just kind of a mathematical term. And each different basis has advantages. And there are code books. These are used in deep learning, building code books, sparse codes. We'll get into a little bit of that later. So you can see there's many ways to describe a feature, depending on which space you choose to work in. So here's a simple taxonomy that I put together at one point in time, and I think any good engineer reserves the right to argue with themselves. So I still argue with this diagram. But the main points to note here are that we can take one slice of the problem and make three axes. So one of the slices, the one at the bottom here, is the spectra. Are we dealing in pixel intensities? Are we dealing with color information? Are we dealing with gradients? Are we dealing with a multivariate set of a combination of color gradients or whatever? Or are we dealing in a completely new basis, a sparse code set? And I'll get into that, so keep that term in your mind as we go. We'll get into that a little more later. So that's one axis. Another axis would be how dense are we looking for features in the image? Are we looking for these global features, regional, or sparse features? And another axis is the shape and pattern. And I'll start at the top. A lot of the trendy descriptors, maybe SIFT, orb, freak, a lot of these descriptors define a region of pixels, and then they look at that region and develop statistical relationships, sometimes following the way the eye works, sometimes using just random samples. There's many ways to come up with shapes and patterns from which to develop a feature. Polygon shapes, rectangular shapes, circular shapes, and the feature description methods that people are using run the gamut. I'm not here to say which one's better because anything can be tuned and tweaked. I'm just, again, we're walking through the Museum of Technology as it is today. So within this taxonomy, this is kind of an eye chart, I realize, but it's in the slides. It's just to point out that within the field of feature description, there's a lot of things to consider, a lot of variables people consider when they're trying to design a feature, a new one that nobody has designed, or when people are trying to use a feature. And so we talked about spectra. Are we talking about pixels? Are we talking about gradients? Are we talking about Fourier frequencies? What are we talking about? Do we need interest points? Some methods go through the image and they look for these interest points. And then at that interest point, they describe a larger feature around it. The interest point may provide a rotation vector so that if you spot the same interest point again, you can determine the angular orientation. Some methods don't use interest points at all. Some methods only use interest points. So there's a whole gamut of things that people are doing. Then there's storage format, data types, how much memory, what's the memory footprint, shape, pattern, density. We'll get into some of these things. So there's quite a range of methods that people are using, and so a taxonomy was interesting for me to go through and put down. So again, we talked about some of the feature families. I like to call them families. And so we have what are called local features, and this is where we get into things like SIFT. What SIFT does is it finds interest points within an image pyramid, so it's a multi-scale representation of the same image. Start with the base image, then multiply it by 2 to get a 2x version, then cut the 1x version in half so you get this pyramid of different resolutions of the image. And SIFT goes through this pyramid and it tries to find maxima points. In other words, gradients, so to speak, maxima points within the pyramid where the maxima spans the pyramid level so that it's a true scale. It's called the scale invariant feature transform, right? SIFT. So the idea is to look for these maxima points in scale and then develop a feature around those. That's a case where a local interest point is used as the key. So a SIFT recognition pipeline can recognize some kinds of objects maybe with 5 or 10 or 20 of these points. It doesn't need to look at the whole image. It just finds a collection of these points and says, well, if I found all of these points or these little motifs or logos or whatever we want to call them, I've got a really high probability that I have the entire image that these points come from. So that's the idea. That's one of the key ideas behind local interest points. Then with the global regional features, we have things that the eye, the human visual system, knows at a higher level how to recognize. Texture. When I look, the way my visual system works, the way I like to think about it, I look for colors, I look for shape, I look for depth, and the contrast, the gradients. So there's all kinds of things. And that's what the global feature metrics can tell you, just basic information at that level. And then we have shape. Shape all by itself is very powerful, and in some types of vision applications, we want to know the shape. We want to know how round it is. We want to know the shape factors. We want to be able to measure shape and match on it. And then we talked about basis sets. And this is where a feature like the Haar wavelets come in, which we'll get into in a little while. So an alternate to pixels is another basis. Transform the pixels into frequencies or transform regions of pixels into sparse codes. Whatever. So you can see there's so many ways that people have used and are using to describe the features themselves. And it's a big field. So again, there are more concepts that apply to the local feature description family. How do we search for features? Do we search at every pixel? Do we search in tiled regions? Do we search for pixels in one tile, then go to the next tile, the next tile? Do we overlap the tiles by some stride factor to speed things up, skip every 2 or 3 or 5 or whatever? So there's a lot of different variation in the methods that people are using and have used. And you'll hear the term detector and descriptor. And oftentimes when you hear that term, the detector means the gradient or the maxima or some other feature. The descriptor is what you may use to describe the region around that. And some methods just use a descriptor. If you've got enough compute power, why not just compute a descriptor? Forget the interest point. Just compute descriptors everywhere. Don't do it sparsely, do it densely. Advantages. Advantages of the local features. This method is that we can just find pieces of objects. We can compose the pieces into larger models. We can measure the distances and angles between the features and develop a model that way. So we have a bunch of logos and motifs that are describing the object. It's one way to do it. So here's an example. I'm trying to illustrate here the different kinds of local features that can be interesting. A ridge, a triangle, 3 lines coming together, 2 lines in parallel, a curve, a larger blob. And this is some information from the book in Appendix A. There's an analysis of synthetic interest point patterns and how 10 common detector methods are able to find the patterns. And if you don't know anything about detectors, it's interesting to see that they all do different things. And in some cases, the same detector goes across the same image looking for the same pattern, and sometimes it finds it and sometimes it doesn't. So other times you use a detector and every single time it detects the feature. And there are many variables, ways to tune these. It's quite interesting. So this is sort of just like a a challenge for someone if they wanted to just get familiar with the detector methods. And this is a picture of my old ES-175D. Any guitar players? I don't have the guitar anymore. And simply by adjusting the contrast of the image differently, a different set of features are detected. So pre-processing is key to many of these detector methods to seeing how well they work. They're very touchy. So again, we talked about local pixel features. You can see I've illustrated that with two types on the top row. On the left, we have the brisk feature, which divides the, on the left you can see the blue circles. Each of those is a different size. And so the way the human eye works, a lot of people believe, and it makes sense to me, in the center we have the fovea, and there's a lot of receptor cells in there. Then as you go farther out from the center of your field of view, you have the peri and the para. There's different amounts of detectors available. So that's what BRISC does. It tries to make a descriptor in the center and then have larger and larger size circles to integrate together to get lower resolution as you get farther away from the high resolution in the center. So it's a variable resolution descriptor. Like when we look at something, we kind of make saccadic motions, or our eye will move around and we will look at something, and we're sort of focusing and dithering around on something we're trying to learn, but we still have periphery vision. It's just not as in focus because that's not where we're looking. And that's what some of these descriptor methods are trying to mimic. They're trying to mimic the way the eye works. And then on the bottom row, we have the SIFT and the Haar methods, histogram of oriented gradients. And if you look close at this image, you can see oriented gradients describing the edges that outline a person. So people are having success in various applications using different methods. Then we talked a little about the other family, global and regional features. And some people use histograms, for example, that bottom left image, just having different levels of focus on the pixels themselves. So if we have pixels that are very much in focus, we have one histogram. If the pixels get a little bit blurry, the histogram changes. And so by taking the same image and having various levels of blur, you can create a set of histograms that describe that feature under various levels of blur. And histograms can be taken in a radial fashion. And on the right side here is an illustration of a spatial dependency matrix. Essentially, that's just looking at the relationship of pixels to each other and then plotting the four orientations. It's just one way to describe texture. So there's so many ways to do this. And the book describes several. And the literature that the book refers to describes even more, and each of those papers describe even more. Then there are shape features. And for example, if we look at this top right image, we see a circle. If we take and sweep a radius around and we plot the endpoints of that circle, we get a sine wave. If we have an object that is slightly off round or has a flat spot, then we can plot that as well, and it diverges from the sine wave. So if we do a Fourier transform of this, we did this one time on an automatic wafer prober. If anybody knows what a wafer looks like, there's a flat spot, at least one flat spot, oriented with the crystal of the wafer. And so we wanted to probe these wafers. We took them out with a robot. We take them out of the carrier, put them on a wafer chuck, and then we have a sensor that runs around the edge, and when it hits the flat spot, you see we have a divergence from a perfect circle. So just by using the sensor to measure the circularity and a Fourier transform to plot the results, we could figure out where the flat spot was on the wafer, so we could put it on a wafer chuck to do a final line with a pattern recognition system. So many methods to describe shape. You can see these malachite pieces here. Each one of those has a perimeter traced and it's labeled. We can find the area perimeter centroid. So these are other features that people are using. Then we talked about basis features. And the top left image shows Haar features. And a Haar feature is essentially a rectangle where all the pixels in the rectangle are integrated and you get the average value out of the rectangle. So you lose all the fine detail. But for some applications, they've been used very effectively to find the regions of a face, for example. A lot of early work in face recognition did very well using the Haar features. And so you have these rectangles that are adjacent to each other in different orientations and different sizes. And then we talked about Fourier domain. Engineers know what that's all about. The 2D Fourier spectrum of a shape has a pattern. And this chart on the right here I put together as I was doing a lot of the research. And I'd never seen anything quite like this chart, but it kind of made sense to me. Probably made sense to people who understood some of these features already. But if we look at the way this chart is oriented, at the bottom left, we have the basis feature set size. So that's the x-axis, is how many features are in the set, and the y-axis is the level of reconstruction detail possible. So if I have an array of pixels, I can exactly reconstruct that image just by copying the pixels and moving them. And that's also shown here as discrete pixels. If I have a continuous real scene, I have infinite resolution. It just depends on how good my optics and my vision are. If I go way down to the other end of the scale, we have basis features. So I can describe the image using basis features. I can describe an image using the Fourier spectrum. That's how JPEG works, for example. JPEG takes a discrete cosine transform and can reconstruct an image just from those waves in a different basis. So the idea with this chart is just to show that there are many different bases that can be used to represent the image, and there's advantages and disadvantages to each one. Sometimes it's a computational advantage, sometimes it's a description advantage, whether it's the space or the accuracy. So these are other ways of describing features. And I put this slide in because for someone who is trying to design a real system, I really think this is key. If you look at the academic research, CVPR, IJCV, all these conferences where people are publishing papers, they're picking on just a few of these invariance attributes, and they're trying to extend the state of the art a little bit. So they can be tedious reading a lot of the research. But for someone who's designing a system, this is one good place to start. And so on the left, there's a box for illumination. This is the key attribute, I believe, for any imaging system, for any computer vision system, because the source of the images is light. And is your descriptor invariant to uneven illumination? We're just reading through here. Is it invariant to different levels of brightness? Is it invariant to contrast? Is it invariant to vignetting, the darkness around the edge? And the same for color. Incompleteness. Can your descriptor track and locate objects under incomplete conditions where a part of it's cut off? Maybe some of the features are gone. Is it, can it track position? Can it be invariant over the thickness of the edges? All of these different attributes. Is it invariant over geometry variations? So this is one good place to start, and this will help you to guide the design of a vision system. You just decide, do I need to be clutter invariant? Do I need to be occlusion invariant? Do I need uneven illumination invariant? What are these invariance features you need? And oftentimes, the environment can be corrected to compensate for the descriptors. So let me give you an example. If we're looking at a factory that processes apples somewhere downstream after they've been washed and they've kind of been separated, I can control the illumination in that factory. I can just tweak it to get my vision system to work. I don't need to write extensive algorithms to measure the spectral characteristics of the light and the value of the intensity and do adjustments on every frame. No, I just move the light around and I get new lights installed, you see? So by defining these invariance attributes and figuring out, do I need to change my environment? Well, some environments you can change, some you can't. Or do I need to pick a different feature description method? That can be very, very key. Again, if we look at different applications, this slide just lists different criteria from the invariance and robustness list on the left, and then 3 different applications: industrial inspection, automobile identification, and multi-view stereo. So the question is, how do they compare with what's important in the way of invariance? And they're all a little different. Vision pipeline models. Now, as we tie together a complete vision system, I'll try to walk slow here because this is where it gets really interesting. From what I understand, some of the early Google visual search would use histograms as an aid. In other words, does this image have a histogram sort of like this one? Hey, yeah, it works maybe 20, 30, 40% of the time. Well, that's better than nothing. So what would the vision pipeline look like for that? It wouldn't be very big. And then if we go all the way to the other end, we have the machine learning. Those pipelines can be very deep, and there's many different ways to tune them. We'll talk about that in a little while. So let's sort of go mid-range here, and this is maybe how an SoC vendor would think. So at the beginning of the vision pipeline, we need to process the sensor. Everybody has their own way to do that. There's geometric corrections, there's lighting corrections, blur, focus, all kinds of secret sauce corrections, deep pixels, all kinds of things that people are doing there. So usually we have special processing that's needed. Usually people just rely on the camera vendor for this. Then if we go to the next step, we have typically image pre-processing. We have an image, it came from the camera sensor, they did everything they could with their DSP. Now, is there anything we need to do to this image to make it more amenable to measurement? Do we want to adjust the contrast? Do we want to do something to the image? Do we want to zoom in? Do we want to crop? Do we want to, what is it we need to do? And again, that's guided by your invariance criteria in part. Image pre-processing, as I demonstrated on a previous slide, really affects the kinds of features you can find. If the pre-processing is set up good or bad, that determines in a lot of cases whether the features can be found effectively. And again, some features are more resilient to different invariance criteria. So pre-processing is another part of your pipeline. Then you may look for global metrics, and these may even guide your pre-processing. You know, looking for the brightness levels, things like that. Then we may have local feature metrics. We talked about what those are, the ones that either look in tiled regions, they look in squares across the image, or maybe they scan the whole image for the interest points. Then we have the most complicated part is the recognition, training, and learning. That's where we start, in my opinion, to go outside of computer vision. Now we're into machine learning. And so these fields work together. Just like image processing is a little bit separate from computer vision and it works with it, it's the same for machine learning. And what I have shown here to kind of illustrate that is a micrograph of a brain. And I'll try to be brief, especially in the presence of the experts, Ren, who have studied and published extensively in this area. The brain works with, there are neurons that are fed by different pathways, different sensors or other neurons. So they're all connected. This neuron may have inputs from several neurons, from sense organs, from your eyes, whatever. And they form these complex networks, and some of them get bigger and smaller. And what they do is when they synthesize their inputs, they fire. And the firing, based on the best neural science we have, is more like a binary pulse. In other words, it's not, I sort of think this is what it is. It's, no, they fire. They say, this is my best guess at what it is, based upon what I'm trained, based upon what I know. That's what it is. And this is only one of the methods, but it's the hottest thing right now on the planet. Ren was just saying how the stock goes up 2x when you say you're doing, you know, this type of research. Hinton, he mentioned his company was bought for $500 million by Google. So do a startup. You might get rich on this. Jan LeCun went to Facebook. And I corresponded a little bit with him. And he's given me some pointers into some of his research. We'll get into a couple things in a minute. So again, the idea here with these neural nets is they've been studied and modeled for a long time. In fact, I was talking to Jan one time, and he was saying, for a long time, everybody hated our research, and they wouldn't even publish. We would send papers to CVPR, and they'd just reject. So he went into the NIPS community. You know, they sort of did their own thing. Nobody wanted to know. And then all of a sudden, everybody wants to know. And I think there was a special session at CVPR just on convolutional neural nets and deep learning. It's amazing how this all changes. But this is not. This is related to the feature metric itself. In fact, let's go to the next slide now and just, I'll stay on this one. So these systems, I'll get into it in the slide after this, they have certain features they look for. Again, there's a feature And then there's a pipeline, and there's a specific pipeline that's used in these types of systems. And then finally in our pipeline, we may augment reality, we may re-render something, or we may have a process control system. So there are many pipelines that you piece together to solve the problem based upon the invariance and robustness that you're looking for. And if you look at it from the SoC level, on the left we may have couple cameras. A lot of systems now have more than one camera. And they typically go straight to a DSP, some type of DSP to process the pixels, do the sensor processing. Then there'll be a GPU. If the GPU has enough compute units, if you're an NVIDIA person, if it has enough CUDA cores, if you're an Intel person, you might say EUs. There's no common way to describe it. But if there's enough horsepower in the GPU, then you can throw a problem at it. But a lot of the GPUs in some of the smaller phones, the price of getting in and out of the GPU exceeds the benefit that the GPU can deliver for processing because of the way it's set up. So then we may have a bunch of CPUs, we have different types of memory, and cloud servers to talk to, fixed function hardware accelerators, taking your code and putting it directly into an FPGA, whatever it is. So one of the things that architects need to consider is, am I optimizing for performance, for power? If I'm designing an SoC, am I optimizing for die area? And these are some of the variables you've got to work with to make your pipeline. And again, there's different types of pipelines. If we want to measure automobiles, let's say I have a camera above my stoplights and I want to look down, I want to try to recognize what kind of car is passing under, I want to count the vehicles. So I'll take 60 more seconds then. And we talked about the convolutional neural nets, and a lot of them use pixels, squares, convolution masks, and they step around. Jan LeCun has also experimented with using Fourier space for the feature. I just read another paper where they're using SIFT features for the feature. But these features are combined in a hierarchical way to where you reach the point of having enough smaller features that have been pooled and recognized together to the point where you can recognize a larger object. So again, the architectures for these pipelines, they're all different depending on the application. So in summary, we talked about feature families, attributes, the different pipelines, and we only touched on the machine learning and training. That's a huge area all by itself. Key takeaways: define the invariance and the robustness attributes. That will help you when you're designing a real system. Keep in mind there are many ways to reach the same goals. You can optimize based on performance, power, whatever. Many ways to do it.
Thank you very much, Scott.